Okay, and finally what I'd like to do is I would like to talk about the tangential and the normal directions. So we have these things, the velocity and the acceleration that we talked about last time for a trajectory. So the trajectory is a boat moves around a path, and at each point we can assign him a vector. The trajectory is the booklet we look up that point in. So we say, okay, I want to know where the boat is after 2 hours. Well, we look up and that's T1, so we can find this S1 of T1, S of T1, excuse me. That is the position of the boat there. We just look it up in our trajectory book, right, our log book, which is the trajectory. So that's a good way to start. Next, we found the velocity and the acceleration by kinematics using this position function. So we use the definition of the velocity. This is really just the definition of the velocity. We use the definition of the acceleration. That's the definition of the acceleration. This is all in terms of all that vector stuff we did. And we're able to determine the velocity and the acceleration. It's good. That's good. We want to be able to do that. Next, I'd like to find a couple of special directions. One of these directions is fairly simple. It's the direction of motion, right? So this is S dot, right? This vector here. So we want to find this tangential direction, right? So sometimes I'll call it t hat, but let's try to call it v hat, right? Because it's the direction of the velocity of the boat. It's the direction of the velocity of the object. That's all the tangential direction means. And we're going to need to recognize what that direction is sometimes because certain forces act in the direction of motion of the boat. You could think of two things for the boat. One would be if this is a fixed propeller craft. When you turn on the propeller, it only pushes you towards the bow, right? Pushes you in that direction. It pushes you in the heading of the boat. It doesn't push you in the course of the boat. The course is the actual velocity, but it pushes you in the heading of the boat. So that might be a little bit different, but let's pretend there's no difference there. And then the drag will always be in the opposite direction. The water resistance will always be in the opposite direction of the motion of the boat, which means it's in the direction of the boat, right? You need to find that tangential direction. So there are certain forces that we'll need to understand how the boat is moving to use them, because we need to know which direction to apply the force. So here we're going to go ahead and find this. So we say the direction of the velocity is the velocity divided by the magnitude of the velocity, right? That's fine. That's simple. That's just what the magnitude is, right? Or the direction is, right? Direction is the vector divided by the magnitude. You end up with a unit vector, and it's in a direction like this. It's just going straight. Simple. Not a problem. The normal direction is going to be this perpendicular direction. Let's see. If we were to use the third direction here, which would be z, right, up here, then which direction are we turning? We'll be turning to the left, actually. So the normal direction is technically this way. Normal direction is to the left, because the normal direction, which is perpendicular to the boat, perpendicular to the direction of travel, we find with the cross product, z hat, because we're in x, y, z is the third coordinate, cross the v hat, cross the tangential direction. So this is actually the important normal. There's another normal called the binormal. We'll let you wait until you get into mechanics to deal with that one. So we take the cross product here, that gives us this thing. Now we looked at the cross product previously. The the cross product would be something like I, j, k. Z hat would be 0, 0, 1. The velocity would be Vx, Vy, 0, because it's in the plane. And so we can use this to find the velocity, right? Just do the cross product. There, no extra room here, so we won't talk about it too much. So these are the definitions again, just vector divided by magnitude. So t hat is the direction of the velocity vector divided by the magnitude of the velocity, or your speed. B here means binormal. If all of the motion is occurring in a plane, the binormal direction is the direction out of the plane. Right? It's the third direction. In this case, that B is Z because we've got an X here, got a Y here. Z is coming out. So the binormal direction is the direction perpendicular to the plane, which means it's the Z direction. Okay, so let's see. Here's a rule. It's out of the plane of the motion. That means if we're in the XY plane, it'll be Z. If we're in the YZ plane, it will be X. And we won't deal with an XZ plane. We'll only deal with XY and YZ because those are both right-handed, I guess. So now I'd want to figure out the tangential direction. Probably it would have been nicer for me to do a third way, right? Probably would have been nicer for me to have given myself some numbers here. Let's see, what do we remember from before? Remember the velocity. We need the tangential direction. Remember, for the tangential direction, it's derivative of the velocity, or it's the unit vector in the direction of the velocity. So we take the velocity vector and divide it by the magnitude. So we want the unit vector in the direction of motion, the unit vector pointing along the direction of motion. So S dot is 2d over t squared t minus 3a over t cubed times t squared z hat. The magnitude of S is the square root of 2d over t squared t minus or plus 9a squared over t to the sixth t squared. Okay, so we have S over S. Let's see, what do we do here? We can pull out the t to the sixth here so that we have in the denominator square root of 2 d squared t squared. This is probably square root 2. Take care of that one too. Plus this has to be a 4. This is 9a squared times little t squared. I've pulled out a little t here because they're multiple squares. And then I have, so then I have t cubed. I multiplied both sides, but I pulled out a t to the 6th, 1 over t to the 6th. So I have t cubed, so I have 2d that's right, 2dt I hat y hat minus (3at) z hat. That makes sense. Okay, so we've got that unit vector as it's changing. So you see this tangential direction is changing. Then we want to find the normal direction, right? Not the binormal direction. The binormal direction is coming straight out at you. Want to find the normal direction. This normal direction, because it's confined to the plane, is going to be equal to y and z there. So x hat cross t hat. And the trick here is going to be, if you remember what it looked like, to do this with unit vector notation, because it's going to make life a lot easier. So I'm just going to call this over this y1 and this one z1 or something like that. Y1 y hat plus z1 z hat. So that's going to be equal to, let's see, y1 x hat plus y hat plus z1 x hat cross z hat. Okay. X hat cross y hat is z hat. X hat cross z hat, we've skipped one, so that's minus y hat. So we're going to have z1 here minus z1, so we have 3at in the y hat direction plus 2d capital T in the z hat direction over the square root of stuff. I run out of screen. 2dt squared plus 3at cubed. So that's all we do, is first we take the derivative, then we take the cross product, and we're fine. Have to, divide by the magnitude. That's not really much of an ask. So those are the two directions as this moves along. I'd like you to do the same thing with your problem, right? So you've done this, if you just use this problem a couple of times, which you find the tangential and normal direction functions as this thing moves along, okay? And yeah, go ahead and turn that in and life will be good. Thank you very much. Bye now.